And so I'm going to show you here some data from a parallel study done with Elliot Wimmer, who was my first graduate student, actually. He's continued. He's now sort of Tom's relative. He's postdocing with Russ Poldrak. And the questions we were interested in asking here are, do reward signals in the striatum related to sort of cumulative average, do they vary as a function of episodic memory? Basically, we want to say, are these two things happening in the brain completely in parallel, or do we see some trade-off between them when we're looking at what's happening in the brain? And how do rewards shape hippocampal episodic memory mechanisms, in the sense that do people's memory for different events change as a function of reward, average reward? So I'm going to show you data from a parallel sort of task here. Again, here what we're going to do, though, is we're going to actually measure people's memory explicitly. So the same kind of task where people are choosing between here blue and green squares. And what we're doing here is taking, again, this canonical kind of bandit task to measure reward learning. And I want to tell you a little bit more about how we analyze these data to give you a feel for the kinds of questions we can ask with fMRI about what people are actually learning and how it happens in the brain. So this is the trial structure. I showed you that. You have sort of hopefully a good understanding of what happens when you walk into the lab. And this is the variability in the payout, which I already described. So on any given trial, someone can be correct or incorrect, right? Someone can either win money or lose money. But what we can do is actually look then trial by trial, not just at that binary outcome, win or loss, but we can actually look at whether that win was expected or not. So I'm not going to show you some of the equations that we use to derive this, but we use a very simple reinforcement learning algorithm, mathematical quantification of what we refer to as prediction errors trial by trial. And that basically refers to the fact that if you chose the blue square and happened to win 4 times in a row, when you choose the blue square in the 5th time, you have a high expectation of winning money, right? If you win money, it's a small surprise. You expected to win money on that 5th trial. If you don't win money, that's a big negative surprise because you expected to win money. So that suggests that even though the outcome on that 5th trial is either a win or a loss, we can calculate your expectations on that trial based on your own individual history of choices and outcomes. Okay? So that's what we do. That's what we do with this sort of Rescorla-Wagner reinforcement learning algorithm. And what that gives us, the reason that's so it's important for a number of reasons, but one of the utilities of that, one of the reasons that's useful to us, is now we can look on each trial at the prediction error for that trial. How surprised were you? How surprised was each subject in the task by the outcome on each trial? And that's interesting because that now provides us with a lot of variability. We can look at whether that surprise signal is meaningful in terms of your behavior, and we can look at where in the brain do responses track with the magnitude of that prediction error by how surprised you are on a trial-by-trial basis. Okay? This is something that people have developed for probably about almost 10 years now. And the reason it's useful for fMRI in particular is it provides us with a parametric regressor. We can now attach a number to each trial of the task, of the magnitude of that prediction error, and use that as a regressor against the bold data from fMRI. When people have done this, many people have done this before, the result that's been reported probably thousands of times now, maybe that's an exaggeration, maybe hundreds of times, is that this quantity of a prediction error correlates with activity, with bold activity here with fMRI in the ventral striatum. And that's sort of the most ubiquitous result, the most common result that is found with this sort of task. And this is an idea that was developed by John O'Doherty and Nathaniel Dodd, this sort of application of reinforcement learning models to fMRI data. One of the reasons it's important, as some of you here probably know, is that it makes contact with what we know that midbrain dopaminergic neurons are doing in animals during learning, sort of a pretty reasonable consensus that those midbrain dopamine neurons are computing and signaling this kind of prediction error quantity and sending that signal to the striatum. So Nathaniel Dodd, John O'Doherty, and some work by Tom and others has shown that we can see that in humans, you see a similar correlate It's a really, I think, fascinating case of where a very simple computational model links single neuron data with human fMRI and with behavior. So that was sort of just a little bit in parentheses to say this is the approach that we're adopting here. And what we want to ask now is what happens to this very common striatal reward prediction error signal as a function of whether people remember single trial events or not. Does this explain those single trial memories as well, or does it not explain them, and does it vary as a function of episodic memory? So to do that, I'm going to give you a very short tutorial on how do we even look at memory with bold data with fMRI. Okay. So now I'm going to show you in many ways the equivalent of from other chapters of our books, right? How do we measure episodic memory with fMRI? And here we take a very simple kind of logic that's been used in the memory literature, nothing about decision making yet, where you ask people to memorize or just look at a series of images. Imagine you're looking at pictures of scenes, and you're asked as a subject to determine whether those scenes are outdoor scenes or indoor scenes. There's one scene, there's another scene, there's another scene. You go home, they ask you to come back the next day or keep you there an hour longer, and then you're given a surprise memory test. In the memory test, you're shown a bunch of scenes. Some you saw before, some you haven't seen before, and you're asked to say whether what you saw before, whether everything you're shown here you remember having seen before or not. Okay. So now we have a behavioral marker of whether you successfully formed a memory or not, and we can use that to backsort these data, and we can look at trial by trial when you were looking at these scenes. Is there something different happening in your brain for those pictures that you later remembered versus those pictures that you later forgot? Okay. So we can take a very clear behavioral marker of successful memory and ask what happens in the brain that's associated with successful memory formation. And here, this is most certainly over thousands of studies. The most common result is that we find activity, bold activity with fMRI in the hippocampus that is greater for events that were later remembered than events that were later forgotten. Okay? And this has been shown many, many times. And so what we wanted to do here was really kind of merge or marry these two approaches to ask, can we use this sort of classic measurement of memory to get a handle on what's happening in how the striatum is encoding memory for rewards? So back to our task here. What you're doing here is, again, choosing between blue squares and green squares. You have objects on the squares you're choosing between. This is very similar to what I showed you before. But what we're doing now, we're not giving you the opportunity to choose between them again. We're just giving you your monetary outcome. And instead, we bring you back for a surprise memory test. Okay? And in the memory test, we show you all the objects you saw. You only saw each of them once, and we show you an equal number of objects you've never seen before. And we just ask you, do you remember seeing this before, and how confident are you in that decision? So now for each trial, we have a marker of a prediction error about the reward, and we have a behavioral marker of memory for that particular object. Again, we have these sort of two distinct behavioral markers of memory, and we can use them to ask questions about what's happening with the fMRI data in your brain. So the first thing I'll show you is this is sort of a slightly more posterior region of striatum, but this is an area of the brain, these are voxels, where bold activity is correlated on trial by trial basis with this prediction error marker. Okay, so these are voxels in the striatum that are showing more activity when you are pleasantly surprised. You didn't expect to win money, but you did, and less activity when you are showing basically no surprise or a negative surprise. Okay, so these are voxels where activity, bold activity, is tracking with your expectations. And now, if we break down this signal and ask, what are these voxels doing? Do they differ based on whether you remembered the event on that outcome or not? What we find is that this classic result that's been shown many times is evident, it's present only for the trials where you did not remember the object. Okay? When you do remember the object, which is generally speaking a good thing to do, we actually don't see any evidence of this prediction error activity in the striatum. Okay, so it suggests that this whole story that many people have shown is true. We can replicate it, but it seems to be true only if you've not encoded the object that appeared. Okay, so it suggests that when you did encode the object, something else is happening in terms of how you're learning about the task and about the reward. So what is that something else? So we show that better memory is associated with a weaker reward prediction error signal in the putamen part of the striatum. So to ask that question, first we wanted to say, do we actually have any evidence in the brain of what we'd expect to see? This is what I told you before, thousands of studies have done. We do a simple subsequent memory analysis. We're looking in people's brains during the encoding, during when they're playing this game for money, and sorting the trials based on whether they later remembered the objects or not, and replicating what many others have shown before. Greater bold activity here in the hippocampus when people remember the objects than when they don't. And this is a replication. This is just sort of a sanity check, so we know we're on the right track. And now we're asking, when people then successfully encode memory, what are they doing? That's different. And what we wanted to ask here is, how does this activity in the hippocampus track or change as a function of activity in other parts of their brain? So what might be happening in particular? We were curious about the striatum. Is the hippocampus sort of potentially suppressing the striatum or influencing activity or associated with activity in the striatum in a way that might explain that trade-off we found of better memory, weaker reward prediction error effect in the striatum? What we did here is we ran an analysis. It's called PPI, I'm blanking on it. It's a connectivity analysis, psychophysiological interaction analysis, that basically asks, where in the brain else are there voxels whose activity during these trials is correlated with these voxels? So we're asking for correlations in changes in bold activity that are specific to one kind of behavior, in this case specific to successful memory. We're basically trying to ask a question that's more aimed at understanding a network of regions, which other parts of the brain are moving along with this part of the brain. And what we found is that it's this exact same region, the other analysis identified in the striatum, the region that's showing changes in reward prediction activity at the time of reward. Here, when people are making the choice, if they're better at encoding memories, they're also using this part of the brain in a correlated way at the time of choice. So it's as if something about the way they're encoding those trials has shifted from choice time away from outcome time, suggesting that there's some sort of trade-off here. So it suggests that there's connectivity between the hippocampus and the striatum during choice that's related to better memory, and that's happening when people are making their choice, not when they're receiving the reward itself. So this, so far, suggests that we have evidence for both kinds of learning, in both behavior and fMRI, that encoding of episodes seems to compete with choice updating and with the striatal reward signals. And we think this is related to sort of broader computational question in decision making, people refer to often as the credit assignment problem. When something happens, good or bad, how do you decide what to attribute that outcome to? You get a good grade in your exam on medieval history in this room. Is that because you studied well the night before? Is it because you slept well the night before? Is it because someone said something nice to you before you walked into the room? So this is a very kind of basic, broad question. And we think that this suggests that there's a trade-off in the attentional selection at the time of reward, where if you've encoded the objects, you are attributing that reward to the object rather than to the deck of cards. We have a series of studies that are looking at what modulates this interaction. And we have a recent paper that just came out about a month or so ago where we've looked at teenagers, at adolescents. We're very interested in how learning and decision making plays out in adolescence. Most people characterize adolescence as being just impulsive and risk-taking and crazy. And there are several studies that have shown that the teenage brain in humans and animals has kind of hyperactivity in the striatum, suggesting they're overly sensitive to rewards. We think that from our perspective, since the striatum is so important for learning, there were reasons to think that that is an adaptive function rather than a maladaptive function, that it's good to be very sensitive to rewards. It might set the brain up to be better able to learn from experiences. And that's basically what we found in this paper that was recently published. We found that in adolescence, there's a greater role for the hippocampus in interactions with the striatum, and that that's associated with better learning from rewards.
Question from a completely different direction. Do you think that you can use this type of behavioral assay and fMRI in order to try to find early biomarkers or early changes in Parkinson's disease patients, for example, since you're looking at specific activity of the striatum?
Yeah. So it's a great question. I'm not sure if everybody could hear it in back, but the question was whether we can use these sort of markers of behavior and learning in the striatum to look at, for example, patients with Parkinson's disease. So about 70% of my work has been related to exactly that question. We've done a lot of work on early phase Parkinson's disease, trying to understand what the implications are of the dopaminergic loss in Parkinson's for this sort of learning. So I have a kind of a separate talk I could give you on that. The short answer is yes. I think this turns out to be actually. I mean, I've invested in it a lot, so I think this is a very important tool for looking at Parkinson's disease for a number of reasons. Patients with Parkinson's disease have no trouble on these sorts of tests with the object memory. In fact, we have some data that patients with Parkinson's disease are better at remembering those objects than healthy controls, but they're worse than healthy controls at tracking this average value. So they can do it, they can learn slowly, but they learn more slowly than control participants. And so this ends up being a useful tool for a number of reasons. One is I think it really sort of is managing to, succeeding in getting at sort of the heart of this dopaminergic prediction error signal, and showing that we can use that to understand selective learning challenges in Parkinson's disease. And moreover, we have a paper came out a couple years ago showing that you find worse learning in patients with Parkinson's disease when they're dopamine depleted, when they're in a state where they have low dopamine. When you give them dopamine medication that elevates dopamine levels, their learning is better. But we recently found that you actually find a similar beneficial effect of just telling people, giving a placebo treatment of medication so they believe they're taking their medication, and that expectation of dopamine causes dopaminergic related improvements in this sort of learning.
But how early can you do it with these patients? So family members who might get Parkinson's trials.
So the question is how early can we see these sort of effects on patients with Parkinson's disease? In our own data, we've only done this with people who are diagnosed with Parkinson's disease. As you know, Parkinson's is a very interesting disease in the sense that patients show up with the first motor symptoms of Parkinson's disease after they've lost 70 to 80% of the dopamine tone in the striatum. Even in those very early phases of diagnosis, when they've lost that much dopamine tone, when the motor deficits are very, very mild, they already show impairments on this kind of reward-based learning. And we've really not gone farther back from that. But it would be, we have the tools to do so. I think it just requires a very, very large sample and a longitudinal study. Yeah.
So I have a question about this really interesting finding you show about the correlation between the striatum and the forgetting and the items that you actually don't remember.
Yep.
So does it have anything to do with what you said that you don't believe in, that about implicit memory or not conscious information? You would think that this information has not been used, right? But it's been used.
Right. So Galit's asking about how do we think about this, the fact that we don't see this striatal reward prediction or response when people have forgotten the object, and whether it relates to sort of thoughts about the extent to which that episodic memory does or doesn't involve conscious awareness. In this test, we're asking people to report their whether they remember it in some kind, in that sense, we're asking them whether they have explicit memory for the objects, and that's the measurement we're using. And so I don't think it doesn't really directly speak to that tension, I think, not as much as some other data we have. But I think it does. It's definitely a data point that's kind of a poke in that perfect multiple system picture, because from the classic two-system kind of model, whether you remember something or not should have no influence on whether your striatum is tracking the average or not. And what this is showing is that they're absolutely interrelated. They're interrelated in behavior, they're interrelated in the brain, they're influencing each other, and that there's this sort of trade-off between the things. And we know from other data that that's true even if you don't actually ask people to report their memories. So you don't need to have conscious awareness of the memory to get at that. Yeah. Any other questions? Okay. Yeah.
So your task seems to be like more like a task, in some sense, a task switching task. I mean, which is usually associated with the prefrontal cortex and reminding the Wisconsin something even. Do you see anything in the prefrontal cortex?
Yes, we do. Yes. So I'm not showing you that for various reasons, but we do see in that sense that a lot of this, the flip in the pattern that we see in the striatum is correlated with changes in prefrontal cortex as well, specifically in VMPFC. So I think that sort of, we can talk about that more. I think there are a number of different ways to think about what that means. But yeah, absolutely. We always see changes in prefrontal cortex, one way or another, right? So this is, I think what we don't know about prefrontal cortex is the specificity with which it's tracking kind of one system versus the other. There's some thoughts out there that it might be playing an important role in arbitration. So I think might be relevant here. Okay. Okay. So the next thing I want to tell you about is moving in a slightly different direction. So in everything I've told you until now, I told you we have episodes, something that happened only once. Right? Took my exam here once 20 years ago. And I told you about averages for things that happen 10, 20, hundreds of times. Right? In everyday life, most of the situations we encounter are somewhere in between. Most events are not completely rare, nor do they happen over and over again. In many ways, I think those are the most interesting kinds of problems we have when we think about how to use past experience to guide our decisions, or these things sort of somewhere in between, where we want to leverage memory to guide experiences, but we don't have a very, very rich knowledge of many, many experiences that are relevant. And so one question I've been very interested in is for these sorts of events that have something in common, like being in the same room for a second time 20 years later, what happens to the memories and how do they get connected? And do they get connected? And what does that mean for how we use those memories to make decisions? So how are anything greater than one related episodes integrated? We think this is really the question that's at the core of how we form semantic networks, how we form concepts, how do we sort of build from one episode up to broad knowledge about the world. And the challenge here, right, is that to guide decisions, we know that memories must be useful, but often we don't know in the moment which memories we will need to use later on. Right. So when I took my exam here 20 years ago, I had no way of knowing that I'd be standing here 20 years later speaking to you. Okay? And yet now I'm able to go back and retrieve that memory and sort of bring it to mind when I'm here. And yet when I formed it, maybe I was in this room 10 other times that I just don't remember at all. So how do we know? One broad hypothesis for how we can resolve this basic tension between needing to remember things that are important without knowing in advance what will be important later on, is that reward, I think also many other things that are important, elicit reactivation, and that reactivation supports the integration of memories to guide later decisions. Okay, so the basic idea is that by being here in a an important context for me. That's bringing back to mind my memories of me being here 20 years ago, and that by bringing that memory from 20 years ago back to mind here today, I'm now integrated and linking between those memories so that my memory networks have sort of reconnected events even though they're distant in time. So why do we think this is relevant and important? So the basic idea, I'm going to sort of just show you a schematic here, is that we think the hippocampus engages in what I've referred to based on really wonderful work by Howard Eichenbaum and Neil Cohen as relational encoding. Okay? So here's a schematic. Imagine that this is, I'll actually use you as an example, right? So here you are in this room listening to me, and maybe here's me, here's the room, here's the person sitting next to you. So we have all these elements of this moment in time that your hippocampus is encoding as connected to one another. You'll be back here later for more talks. Who do you have next? Oh, you have Scott Small. That's a great example. So Scott Small is coming. You'll be here. You'll be in the same room. I won't be here, right? But Scott will be here, and Scott will both be in the same room. Scott is also a colleague of mine from Columbia. And so we know that one thing that's crucial for how the hippocampus works is that when it receives partial input, the room, it brings back to mind memories that are related to it based on that common feature. So that can lead to this reactivation. So here you'll be here in the same room with Scott, but based on these common features of the room and me, you'll bring back to mind, whether consciously or not, your memory of being here today. The reason this is really potentially useful and has important implications is by doing so, if you now have, if Scott gives an exceptionally good or exceptionally bad talk, I'm sure it'll be great, then that will now lead to an integration of that memory with this memory and suggest that all kinds of features related to Scott's talk are now going to become connected in memory with features of this talk, even though they never co-occurred. So these features of the hippocampus that it builds relations and that it can lead to reactivation put the hippocampus in a position to be linking memories that were never actually linked in real life. Okay. And the one idea is that this kind of reactivation then supports the integration of memories, and that that's very useful for decision making. It allows you to sort of generalize from one memory to another in ways that you can use. So how would we test this idea? This is related, there's a good evidence for this sort of reactivation in neuronal data from animals, mostly in spatial navigation tasks, but how do we know that that happens in humans, and how do we know that it has any relevance for behavior? So what we do is we develop tasks, computer games, where people form neutral associations, then learn about rewards, and then we ask them to make decisions that require this kind of integration, that require them to bring together information across episodes. And the questions we're interested in asking here are, first, does this integration of memories guide decision? Is there such a phenomenon? It's sort of a fake question because there's good behavioral evidence to suggest that this happens. And so the real question we want to know is, can we kind of track this with a behavioral task? And when we do so, can we find evidence for reactivation in the brain? Can we find any evidence that people are bringing back to mind memories and that they're using them to make decisions? So we tested this idea with Elliot Wimmer, who, as I mentioned, was a graduate student in my lab. And I'm not going to go into full details, but I really would like to explain to you the logic of the task and how one would do something like use fMRI with all its weaknesses and messiness. Can we use fMRI in humans to look at evidence for this kind of reactivation? So what we did here is we used a task called sensory preconditioning, which actually goes back. It's a task that was developed for use in rats and pigeons in the 1930s. But it has this element of reactivation embedded in it, and so we adapted this for human learning. And the basic logic is that we give people pairs of items and that they encode. These are just neutral items that they haven't seen before, but that they co-occur. So they become associated, as people just engage in the task. But then what we do is we take this previously neutral item and now we pair it with a monetary reward. And then we ask people to make decisions about this triangle. Okay? We do this with lots of pairs, and we control for the familiarity and the likability and so forth. So there are a lot of items here that are paired. And we basically ask, do people here have a preference? Do they exhibit any kind of evidence for having any value associated with this triangle versus other controlled for stimuli? Right? So the key thing here is that this triangle, like me in the Scott Small example, this trial was never associated with this outcome, with this monetary outcome. Only this stimulus was, but these two were associated. And so what we think might be happening is that when this reward phase happens, that there's reactivation of the previous learned association, and that reactivation would cause in your minds and brains an association of monetary reward with this neutral triangle that was never actually paired with reward. And if this happens, that would lead to a preference here for that triangle. Okay? So the important aspect of the logic is that this is all completely neutral, but there's a later event that you could not have predicted. We want to see how the later rewarding event influences memory for this neutral object. And so what we do is we run this kind of task and we use fMRI to look at what's happening in the brain here and how it relates to later decisions. And the predictions are that we think decisions will be related to hippocampal activity during that reward learning phase. So we think there should be evidence for reactivation first in terms of hippocampal activity. That should not satisfy you. Hippocampal activity could be related to lots of things, not necessarily reactivation. And we think that those sorts of decisions will also be related specifically to reactivation of those neutral stimuli during the reward learning. Okay? Yes?
About the behavioral task, a simple question.
Yes.
The reward on the neutral stimuli, is it correlate? Do you give a reward on the neutral stimuli? Because during the block, do people learn that
right.
they will be correlated, and
right.
they have a reason to predict the correlation?
Right. So this is a classic case of when you're giving a talk and you try to cut things out, it ends up adding more time than saving time. So let me tell you exactly what people are doing, which answers it. The first phase of that task, those two things are associated only in time. They appear one after the other. It's completely implicit. People are completely unaware that those two stimuli are associated with each other. And then no rewards whatsoever. Okay. Second phase of the task, only that second cue appears, and it's associated with reward. The first cue never appears during that phase. Okay? So basically, there's nothing in the task at all that associates reward with that black triangle. Okay. Other questions about the task? Okay. Okay. So basically, the first finding we had that suggested that this might be happening is a weak finding, relatively speaking, which is that we found that if you look at activity in the hippocampus, bold activity in the hippocampus, you find that activity here in the reward phase predicts later generalization, the later likelihood of choosing that black triangle. But again, that, I think, suggests that there's something crucial happening here instead of here, but it doesn't tell us what's happening here, and it's not yet evidence for reactivation. To find real evidence for reactivation, what Elliot and I did is we said we shouldn't use black triangles. What we should use are cues who have visual properties that we know where to go fishing for them, where to look for those visual properties in the brain. Okay. So we basically used a trick, and instead of black triangles, we used faces, body parts, and scenes. And here we're still using these colorful fractals. Okay. We know where, in which parts of visual cortex, the brain responds to faces, body parts, and scenes. There are specific areas of visual cortex that are specialized for these kinds of cues. So that what that allows us to do is then ask, when people are engaged in this reward learning task, all they're seeing are these fractals, these circle images, and money. That's all they're seeing here. And we ask, is there evidence for activity in the body parts, the face parts, and the scene parts of the brain when people are seeing the associate? This is basically like if I scanned your brain when Scott's speaking, and looked for the Daphna Shohamy regions of your brain and saw any activity there even when I'm back in New York. Okay? Basically asking, is there any evidence of a sort of a leftover or evidence for reactivation of these items when they're not appearing? And the short answer is that that's exactly what we found, is how much activation in this phase of those previous cues, how much activation there is here, predicts how likely you are to think that these cues are associated with reward or to associate them with reward later on.
Do you need to have the reward stage to get that, or familiarity alone?
Yeah, it's a great question. The question is whether we really need reward to get that. So I think the answer is yes and no. The reason the answer is yes is based on data that if you run the exact same task with punishment, with monetary loss, the effect is much weaker and more variable. We don't know why yet, so we're looking into that now. But there does seem to be something about reward that enhances this generalizability. And we think that's interesting just at the level of a phenomenon, because it suggests that it's like something is set up for better in healthy people to better generalize a positive outcome than to generalize a negative outcome. The reason we think this is the answer is also no is we still think this is happening. We think this is basically a fundamental mechanism of how the hippocampus builds memories. It's associations. It's associations and reactivation. It should happen all the time. But we think some things are just more likely to elicit that reactivation, and that reward is one of them. Yeah. Yeah. And it may also be the case that negative outcomes elicit reactivation and generalization more in some populations, such as people with PTSD or people who are high on anxiety. Yeah.
So a bit similar question, but whether it's specific to reactivation. So if you were to scan the subjects during the encoding phase and test for these correlations?
Great question. So we do scan people during all phases, and we do not see any evidence for either hippocampal activity or anything predicting generalization if we look at the encoding phase, or even when we look at the decision phase. So this is the only place where this is the only phase where we find this evidence. So here's the data I just described. Basically what we're showing here is on the y-axis, bold signal in these visual cortical areas representing faces, scenes, and body parts. And classifying trials here for trials that are where people show these sort of integrated generalized decisions, and trials where people do not. Just to come back to this point, we had a review. The short version is we didn't really have a strong opinion. I didn't have a very strong opinion that I wanted to put out there at the time about whether conscious awareness is important for this sort of phenomenon or not. It's a question I avoided for about a decade. We had reviewers who thought this was very important, that this was happening in the hippocampus without conscious awareness. We felt like there's a lot of evidence for non-conscious processing in the hippocampus, and they said, yes, but people don't know that. So we ran numerous behavioral follow-ups that now allow me to say confidently that in everything we've looked at, this happens without conscious awareness. So this is not the case that people are stopping to retrieve memories. In fact, people show no awareness of the associations that are guiding their decisions to begin with. And that's, I think, important from the perspective of what exactly are the memories that the hippocampus is building. Okay, so just to summarize, reactivation supports integration of memories in service of decisions. We find that this happens automatically and implicitly. So your opinion about me will change once you see Scott, whether I like it or not. Luckily, Scott is a fantastic speaker. The integration occurs before decisions are faced. And we think this is really important because it suggests that it's not that when you stop to make a decision about what you're going to do or what you're going to order at the restaurant, that you're stopping and effortfully bringing up memories and trying to think about what you ate there last time. That's not what we think is happening. What we think is happening is that your memories are continuously changing and being represented in a way to be available to you for decisions you're going to make, so that integration already happened, regardless of decisions that you face later on. We have some additional data, coming back to Galit's earlier question, that this involves kind of a network between the hippocampus, the striatum, and ventromedial prefrontal cortex. So people with greater connectivity between these regions actually show less of this generalization. People who have weaker connectivity at rest between this network show more generalization, more flexible in their memory attributions. We don't think this is the only way to make decisions. We have a lot of evidence from other tasks that you can also integrate. You can also stop now and remember what happened 20 years ago, like I've been doing repeatedly, and now I'm going to bring those things to mind at the moment of a decision. And so there's certainly evidence for that. And we now have 2 papers showing that dopamine is really playing an essential role in this process and setting up these reward-based integrations of memories to set them up for later decisions. Okay, so in the last few minutes, I just want to tell you about an idea we have that sort of tries to address questions of how this plays out and how it links to other kinds of decision making. So I started by telling you we're really trying to understand how memory and decision speak to each other across the brain. And I haven't really told you yet what that means, how we think our memories are kind of used to really be computed into a decision factor that will determine the decisions we make. And so I'm not going to show you data here. I just want to kind of lay out briefly the idea. This is in collaboration with Mike Shadlin. And Mike Shadlin studies perceptual decision making, which I've argued with him might be a very different kind of decision. I think that we're just asking people to report what they're seeing perceptually in the world, essentially. But Mike and I noticed a very interesting phenomenon, which is when you ask people to make choices between foods, let's say, what are 2 foods? Hummus and pasta. When people make this kind of decision, how long it takes reflects how different the values are of those foods to begin with. And that in many ways, that can be viewed, formally speaking, computationally speaking, as very similar to the kind of decisions that people are asked to make when they do a perceptual decision-making test. So here's just a cartoon demonstrating the kind of work that Mike Shadlin and others have done in animals on perceptual decision-making. You show people randomly moving dots, and you ask them to decide, are those dots moving to the left or to the right? Okay? Very different kind of decision than the one we usually think about. But what Mike and others have sorted out is that to make this kind of perceptual decision about which direction dots are moving in involves sensory processing. Obviously, you have to sort of detect where the dots are moving, and that then you accumulate evidence about the dots over time until you compute a variable of your decision, and then you basically make a choice, left or right. And a crucial thing in these tasks has to do with what many people, and Mike chief among them, as momentary evidence, the idea that there's something, calculation in neurons over time, accumulating the sensory input until there's enough evidence to suggest that the dots are moving towards the left or towards the right. Okay? So how do we get from there to the kind of decisions that we're interested in that are more complex and based on memory? On one hand, a decision about value, about foods you have to choose between, may seem at first glance to look very similar. You have to process the foods themselves. You have to accumulate whatever information you have about those foods until you can reach a decision between one food and the other. But one idea is that where memory plays into this sort of computing of a decision variable is specifically here, where the evidence is coming from. Because the idea is that when you're looking at the foods or any other kind of decision of that sort, the information about what's valuable to you is not right in front of you. Right? The information really comes from your past experience and from thoughts based on past experience about the future. And so the idea is that we can now know exactly which neurons to look for and which parts of the brain where the evidence should be coming from the hippocampus and entering this decision-making process and should play a crucial role. And so the prediction is that even simple value-based decisions involve memory retrieval, and that should be related to how long it takes to make those decisions. And that's work that postdoc Akram Bakor is working on. Akram worked with Tom when Tom was doing his postdoc. And Akram is now postdocing in my lab. It's all very incestuous. All right, so just to conclude, we can dissociate incremental from episodic influences on decisions, identify which memories are sampled to make decisions, and when they're sampled, obviously beyond memory strength. So what are the kinds of contexts and circumstances in which different kinds of memories are used? We think that the hippocampus plays a very important role in decision making by supporting decisions based on rare or new events. And that broadly speaking, we think the hippocampus is contributing to the formation of a world model, so a rich kind of network of associations that represent what has happened, and based on that, what is likely to happen in the future. And finally, that a complete understanding of decision-making really needs to take into account the neural mechanisms of how memories are built, how they're biased, how they're retrieved, and how they're used. I'm going to end on a quote I like a lot by Daniel Kahneman, who said, we don't choose between experiences, even though we think we do. We really choose between memories of experiences. And luckily, we know a decent amount of how those memory mechanisms play out neurobiologically. We just have to understand how they link now to what we know about decision-making processes. So thank you for listening, and just to thank the people. Yes?
You found differences in brain activity during recognition items and later after. My question is, was there a difference in the brain between items that the respondent identified as seen but hadn't seen? It's about memory. Was there any difference in brain activity about items that it's never seen
and think they saw? Yeah, it's a great question. So, and I'm gonna expand it a little bit. Right? So the question is do we see any evidence of something happening in the brain for false memories, which is something people have looked at. But before I answer, I'm just going to expand it a little bit to say this last bit I told you about integration, where people are attributing value to that black triangle. Right? You could call that a false memory, because that black triangle was never associated with reward, but people attributed reward to it, right? And to me, one question that comes up a lot when I show those sorts of data is, wait, is this a good thing or is this a bad thing? I think the neuroscientist in me feels like there's no such thing. There's brain mechanisms. This is what happens. Sometimes it's good, sometimes it's bad. The psychologist in me wants to understand when it's good and when it's bad, and I think there's you can imagine all kinds of circumstances. So one thing we're doing now is trying to understand, can we get people to generalize, right? What we did here, what I showed you, we kept it all completely neutral. It was up to the participants. We didn't reward them, we didn't punish them. But can we shape people to be in a state of mind where they're more likely to generalize, or can we shape people to be in a state of mind where they're more conservative in terms of their generalization? Very broadly speaking, when we ask people to report memory for the objects, we didn't look in that study at false alarms. There weren't very many false alarms, but other people have looked at that sort of thing. It seems to be associated particularly with bold activity and or lesions to ventromedial prefrontal cortex, where people have especially false kind of overconfidence in having experienced something before when they haven't. And I think that's all related, again, because what look like false memories and errors are usually not random. Right? We falsely remember things that are usually meaningfully, schematically, semantically related to things that we need to remember.
אגב, שאלות בעברית, אם רוצים. יותר קל.
כמה קיבלת בבחינה בימי הביניים? כן.
בעברית.
בבקשה.
כמה התוצאות הראשוניות של האינטגרציה לעומת זיכרון בודד הן תלויות בסוג האוכלוסייה שהשתמשתם בה? אני מניח שלקחתם סטודנטים מקולומביה, אני לא בטוח.
הנחה סבירה. כן, לא, זו שאלה ככה, התשובה הפשוטה היא שבאמת עשינו את זה בקולומביה עם סטודנטים של קולומביה. אחד הדברים המאוד מעניינים, שאנחנו יכולים על כל נבדק בעצם להסתכל על הלמידה הפשוטה, כמה הם למדו את הקשר בין העיגול לכסף, classic conditioning כזה, classical conditioning פשוט, ועל מה שאנחנו קוראים לו generalization או integration, אוקיי? מה שאנחנו מוצאים בסטודנטים בקולומביה, שכולם לומדים את הקשר הישיר הזה בין העיגול לכסף, בלי בעיה, אבל יש שונות מאוד מאוד גדולה, גם בקרב אוכלוסייה שהיא יחסית מאוד הומוגנית. יש הרבה שונות across נבדקים, בכמה הם עושים את ה-generalization הזה. ואחד הממצאים שהזכרתי ולא הראיתי, זה שגם באוכלוסייה ההומוגנית הזאת, ההתנהגות הזאת קשורה למערכות ב-REST, בין VMPFC, היפוקמפוס וסטריאטום. איך כל ההתנהגות והמוח נראה בנבדקים שבאים מנבדקים יותר הטרוגניים, אני לא יודעת. עשינו משהו דומה בסטנפורד, ראינו את זה שם, אבל זה בערך אותה אוכלוסייה. אבל אני חושבת שהממצאים האלה ב-resting state נותנים לנו איזשהו בסיס עכשיו שאנחנו יכולים לנבא מראש מי הנבדקים שעשויים להראות את ההתנהגות הזאת בצורה יותר חזקה, ומי הנבדקים שמראים את זה באופן יותר חלש. יש לנו עכשיו שיתוף פעולה עם בלר סימפסון בקולומביה, שהיא מתמחה ב-OCD ובחרדה. ולהם יש קצת דאטה מ-resting state שמראה הבדלים באותם הרשתות. אז אנחנו רוצים עכשיו לראות אם אנחנו יכולים להשתמש במידע מה-resting state בשביל לסמן מראש מה אנחנו מנבאים פר נבדק עם חרדה על ההתנהגות הזאת. אז זה עוד in process.